Digital video encoding technology has transformed the entertainment industry by giving users on-demand access to vast libraries of free and paid video content. While digital video streams are ideally suited to deliver pre-encoded movies, television programming, and most type of live broadcast programming, video streaming has been much less successful in providing instant access to interactive video game experiences at scale. This is largely because the video codec itself, as well as the servers and networks required for video-based cloud gaming, are not well suited to providing cost-effective interactive gaming experiences at the same high image quality, frame rate, and low latency expected by today's gamers. In this video, we briefly examine some of the technical obstacles faced by video-based cloud gaming systems and introduce an alternative approach to streaming games that avoids the cost and quality issues of video-based cloud gaming systems. As we'll see, this innovative technology does not stream video of the game, but instead interactively streams the game engine assets, that is geometry, texture tiles, and other assets, directly to the client-side game engine software in real time. This method, which we call sub-asset streaming, enables virtually instant access to gaming experiences at unrestricted frame rates and zero added latency. But before describing this new streaming technology, let's examine the limitations of video-based encoding and streaming as applied to cloud gaming. A major limitation of video-based cloud gaming systems is that they cannot effectively use CDNs. CDNs, or content delivery networks, are of course highly evolved networks that enable low-cost delivery of pre-encoded and live broadcast streams on a global scale using inexpensive local servers. CDNs are simply not capable of running the game engine software required by video-based cloud gaming systems. Video-based cloud gaming systems instead require expensive, specialized GPU servers that must dedicate a GPU, several CPU cores, and a substantial amount of memory to each connected user. This is well beyond the capabilities of CDN local servers, which have no GPU and typically use only a fraction of a CPU core and a small amount of memory to deliver video streams and other web page content to a single client. Consequently, video-based cloud gaming systems must incur the capital and operational costs of these more expensive servers in the data center and cannot use local CDNs to avoid the higher cost of more long-distance backhaul streaming. The inability of video-based cloud gaming systems to use local servers also increases the latency between the game and the end user. Server-to-client latency does not typically adversely affect the user experience for streamed pre-encoded video or most live broadcasts since they're not interactive. However, for video-based cloud gaming, any added latency can create significant gameplay lag between the gamer at home and the game running on a remote server. This annoying lag makes games less responsive and more difficult to play. In fact, in the past few years, many gamers have come to prefer very low latency and high frame rate experiences, such as 144 frames per second gameplay, which is not available from video-based cloud gaming systems. Similarly, virtual reality games require both low latency and high frame rates and are consequently not supported by video-based cloud gaming systems. Another limitation faced by video-based cloud gaming systems is that to keep encoding latency very low, they're forced to use much lower quality video encoding profiles than are typically used for pre-encoded or broadcast video. Video encoders achieve better image quality and lower bit rates by introducing at least several hundred milliseconds of encoding latency. For example, spending more time to capture a better delta coding across a larger group of pictures. This figure shows the well-known triad of trade-offs between video quality, bitrate, and latency for video encoding. But video-based cloud gaming systems are unable to use these longer encoding latencies to improve image quality without introducing unacceptable lag. In addition, conventional video-on-demand systems always use a client-side playout buffer of video future frames to buffer against packet loss and network jitter. As shown in this figure, a client-side buffer makes the stream resilient to transient decreases in available bandwidth or to transient increases in latency, which is called jitter. However, video-based cloud gaming systems cannot use such buffering since it increases latency. And the lack of a client-side buffer makes video-based cloud gaming systems highly susceptible to small transient network disruptions that would not affect other video streams. To address the shortcomings of video-based cloud gaming, we've developed a new type of stream for interactive content called the GPEG, Geometry Prompt Engine Group Protocol. GPEG does not stream video, but instead interactively streams the geometric, texture tile, and other game assets to the game engine software running on the user's hardware. GPEG is designed to stream interactive experiences in a way that avoids the intrinsic latency and compression issues of video-based cloud gaming systems, providing a higher quality of experience at a much lower cost. This figure shows a high-level architectural overview of the GPEG protocol, which is implemented as game engine plugins, including encoder, server, and client software components. The GPEG encoder software plugin works within the game engine editor and allows the game developer to easily select all or part of the game for GPEG encoding. In a one-time offline process, the GPEG encoder software effectively separates the game engine executable, which is typically relatively small, about 100 megabytes for Unreal Engine, from the game engine's assets, which could be quite large, exceeding 50 or even 100 gigabytes of data, and often take more than an hour to download. The GPEG encoder converts the game's assets into much smaller sub-asset packets based on their potential geometric and perceptual visibility within the game. These pre-encoded sub-asset data packets are uploaded to the cloud for later streaming. The GPEG server software streams the pre-encoded sub-asset packets from conventional edge servers and from CDN. The GPEG server software is a thin server software process which requires no GPU and only a fraction of a core of a single CPU to serve one client. This allows GPEG streaming from virtually any edge server and CDN at a small fraction of the cost of video-based cloud gaming, which of course depends on expensive specialized GPU-equipped servers. During gameplay, the GPEG client game engine plugin monitors the user and camera movements within the game environment and reports this information to the GPEG server software. The GPEG server software uses this information together with conservative navigation prediction algorithms to intelligently prefetch just those sub-asset packets that could become visible to the user and potentially needed by the game engine in the next few hundred to few thousand milliseconds. The GPEG client side plugin receives the GPEG stream and uses it to intelligently maintain a limited cache of sub-assets that are usable by the game engine. Because this cache can be much smaller than a game download or even smaller than a single level load, gameplay can typically begin in seconds, and users can instantly access a virtually unlimited number of games without concerns about local storage limits. Because GPEG prefetches sub-asset data before it's needed, it does not introduce any latency like video-based cloud gaming or command streaming approaches. Since GPEG streaming uses the client game engine and hardware to render, it does not introduce any video compression artifacts or place limitations on frame rates. The GPEG protocol and sub-asset streaming API leverage the fact that game engines use many common asset types, such as static meshes, skeletal meshes, textures, and others. And these assets are common types because they're expected by all graphics hardware and the lower level APIs that subserve that hardware. Because it's implemented as game engine plugins, GPEG is designed to also accommodate asset types that may be unique to a particular game or game engine. This is a visualization of the GPEG geometry streaming process in Unreal Engine showing geometry prefetch. The streaming of texture tiles here is not shown just for clarity. The red sphere is the user's current camera position, which is monitored in real time by the Concurrents server software. The blue and green boxes are view cells, which are pre-generated by the Concurrents encoder. The view cells define where the users can move in the environment, and they're used to generate visibility-based sub-asset packets. For each view cell, the encoder has pre-computed precisely which geometric and texture tiles of the game will become visible if a user would cross a specific view cell boundary. For example, if the green view cell would be penetrated, then the green surfaces of the game environment are become potentially visible, and they're preemptively prefetched. So the video shows the potentially newly visible or green geometry being predictively prefetched based on the user's potential movements within the environment. It shows the navigation prediction algorithm identifies all reachable view cells ahead and around of the user in real time. And it shows that the relatively small amount of newly exposed or green surfaces in most regions suggests that this new type of stream exploits a powerful source of visibility coherence that occurs as the surfaces of the world emerge and unfold around a user camera moving within the world. This navigation-driven, visibility-based prefetch of granular game engine subassets is the basis of a new type of stream for interactive content. This video has provided a high-level overview of the GPEG subasset streaming protocol. In later videos, we take a deeper dive to examine how GPEG solves the difficult problem of conservative from-region visibility precomputation. We also show how the protocol can use a unique conservative view frustum to further limit bandwidth, and how the visibility-based protocol accommodates moving objects. We'll also discuss how the protocol can use both the potential geometric and the potential perceptual visibility of subassets to improve quality of service while reducing bandwidth requirements.